Apologies, IT issues as always. So practically, the problem statement is size of the model is growing up, right? Which results in jobs running longer, scale is larger, and demand for bisexual bandwidth is larger. So practically, any issue on the fabric being link failure, switch failure, degradation will have larger and larger impact. Theoretically, any failure could lead to complete job failure, and hence will require you to go back to your checkpoint. If you are lucky enough, it's a few minutes. If you aren't, it could be a few hours or a few days. Right? So to emphasize, we need to introduce new technologies that will allow us to converge faster, rebalance faster. Without that, we see performance degradation nonlinear. So as you start losing capacity within the fabric, if you have no ability to rebalance the traffic at the source, it will result in disproportional degradation. And this is goal of the presentation, really to show you how the difference between how fabric would degrade with only local reaction on failures versus global knowledge. And there are a variety of ways to signal this through control plane, through data plane. I'm not going to go into details here. So practically, as we said, the resilience KPI in AI training have very, very special meaning. If your behavior is such that your job fails, you go back to checkpoint, right? So you lose a lot of work. And it's not only convergence in traditional space, where, I mean, networking people, we will say convergence is when you lose something and you use alternative paths. Here we're also talking about densely meshed topologies. So usually when you lose a link or a couple of links, you didn't completely lose the reachability. You lost the bandwidth. So ability to react on this lost bandwidth somewhere further in the fabric is fundamental to steady performance. So even when you have less bandwidth, you still want to be able to finalize your job without significant performance impact. The high-level overview of this. So traditionally, on a switch, we react on local conditions. We react on key occupancy, we react on the amount of traffic on the port, and we can load balance traffic accordingly. Whether you do it through adaptive routing or DLB, there's a couple of different technologies that are capable of measuring key occupancy and rebalance traffic accordingly. So the kind of goal of this solution is to augment this behavior with global knowledge about either link failure, node failure, or any other problems here. So we are going to look at a case. In this case, the traffic patterns bisection with, very simple, really, 96 NICs connected, 96 GPUs connected to 3 switches, and 3 switches having 96 links up to the spines. And what we're going to do here is start failing links in different matters. So you see a couple of different failure patterns, and we will see the results. In this case, what you see is histogram of system that has global adaptive routing enabled. What you see here is exactly what we want to see. It's the desired behavior. We see gradual degradation. And in the next slide, we will see how it works if you don't have adaptive routing. So practically here, you see as you start failing more and more links, independently of where you fail them, the degradation is gradual. What you lose is really amount of bandwidth that you have physically lost. It's not more than that. So let's take a look at all-to-all, which is really communication from every switch to every switch. In order to make this result kind of higher fidelity, we also compute in local bisection. So since we've got 4 switches, 1/4 of the traffic is going to stay local under the leaf, so we don't compute it. Since we've got 2 spines, we have half of traffic going through each spine. So in this case, our bisection is 0.66. Practically, what we want to see here is as we start failing links, we want to see gradual degradation. The amount of traffic each queue pair should be able to send and receive should be that of bandwidth totally available minus bandwidth lost. However, as we start looking, and here we see it from nickel perspective, as we lose 8 ports, suddenly we drop to half of the bandwidth. And as we fail more links, we see disproportional degradation of AI workload. On the top green line, you see the desired behavior with global AR enabled. So you see that the degradation in job performance is exactly that of bandwidth lost. So again, it's to show you importance of knowing globally in the fabric what's available further away from you. So as we said, the problem here is that the degradation is drastic and disproportional. And actually, when you lose complete spine, so 16 links from leaf to the spine, your performance is better than when you lose 14. Because practically, if you don't know that you lost links, you'll keep sending traffic, oversubscribe, and drop traffic when you go down from the spine. So global knowledge of failures, very, very important for good performance. And this is view from the application perspective. Right? It's large AI training, and what you see here is the difference between system where global adaptive routing is enabled versus not. So when we bring 50% of the uplinks down, you see degradation of 70% if you don't use global adaptive routing versus 90 if you do. And then similarly, as you bring down more and more links, you see the delta between system that has global awareness versus none growing up and growing. So my call to you, please do understand, just understanding local behavior is not enough for large distributed system. You need to introduce knowledge of what's done at global scale, and this is what we do in Spectrum-X at NVIDIA. So there's more information here for marketing, but it is what it is. So please do take a look. It's really, really important that you understand, because cost of failure is huge. The model's getting larger. The cost of restarting job is getting larger and larger. Make sure your fabric can sustain the load. Make sure that under failure, and there's always a failure, we are going towards 100,000 plus GPUs. There's already cluster running today, 100,000 GPUs, been announced publicly. Right? So statistically, there's going to be more and more failures. And in order to provide fabric and infrastructure that can deal with it, you need more knowledge that's done local. And I'm open for questions.
Questions?
So, Jeff, so you put this as multiple links. So this problem will be introduced only, like I say, when you have multiple links. So if in the deployment you only have a single link, this issue will not be there, right?
In 3 stages or 2 levels, yes. If you go into 5 stages, you'll observe exact same issue, even if you have single links. So practically, unless you're trying to leverage your radix and you go skinny links, in most cases, you'll see more than 1 link between any given pair of switches. It's a common deployment, right? So in this case, you will see the behavior as described. What I'm showing is what we've tested in large AI clusters that we run in Israel, and those are the real results. If no more question, thank you for attention, and hopefully I save 5 somewhere else.